there's something about the moon that never stops fascinating us. It's always been there, hanging in the night sky, a constant companion to humanity since before we even developed language to describe it. But here we are in February 2026, and we're about to do something that hasn't happened in over 50 years. We're going back. And this time, we're not just paying a visit. We're coming home to stay. The story of how we got here and where we're going is not just about rockets and spacecraft. It's about the fundamental human drive to explore, to push boundaries, to ask questions about our place in the cosmos. And it all comes down to understanding one simple fact. The moon isn't just a beautiful object in the night sky. It's a stepping stone. It's a laboratory. It's a proving ground for everything humanity will accomplish in the next century of space exploration. But before we get into the mission details, let me set the context. Why is this moment significant? Why now? What changed? For most of human history, the moon was unreachable. It was a mystery. Ancient civilizations developed mythologies about it. Medieval scholars debated whether it was made of the same material as Earth or if it was fundamentally different. Renaissance astronomers built telescopes and saw craters and mountains. They realized the moon was a world, not a perfect celestial sphere. But for all that knowledge, it remained beyond reach. The moon was 239,000 miles away, and humans couldn't bridge that gap. The moon represented the limit of human exploration. Every ocean on Earth had been crossed. Every continent had been visited. Every mountain had been climbed. But the moon remained beyond us. Then, in the 1960s, something changed. Technology advanced. Rockets became powerful enough. Computers became sophisticated enough. Engineers developed the techniques to navigate to another world. And in one of the greatest achievements in human history, we reached it. In July 1969, Apollo 11 landed on the moon. 2 humans stepped onto the surface, and everything changed. Let me take you back for a moment, way back to 1969. When Apollo 11 landed on the moon on July 20th, 1969, it represented the pinnacle of human achievement. Neil Armstrong and Buzz Aldrin became the first humans to set foot on another world. And you know what they were doing up there? Science. They were collecting samples. They were leaving instruments. They were conducting experiments. It was real, serious scientific work. But here's the thing, we left. For 50 years, we left. We went back a few more times with Apollo, and then we stopped. And humanity has spent the last 5 decades looking up at the moon, knowing we'd been there, but wondering why we weren't going back. During the Apollo program, from 1969 to 1972, NASA landed humans on the moon 6 times. 6 separate missions. 12 astronauts walked on the surface. They spent a combined total of about 300 hours on the lunar surface. They collected 382 kilograms of lunar rocks and soil. They deployed experiments that gathered data for years after the missions ended. The program was a triumph of human ingenuity and determination. But the program ended. The reasons were complex. The initial justification for the moon landing was the space race, competing with the Soviet Union for prestige and technological superiority. Once that race was won, political support diminished. The Vietnam War was draining resources. The economy was struggling. Priorities shifted. Moreover, there was confidence that humans would continue to explore space, just not necessarily the moon. The Space Shuttle program promised to make spaceflight routine and affordable. The vision was that the shuttle would launch frequently, enabling space stations and space manufacturing and regular access to space for scientific research. The moon seemed less important when near-Earth space seemed accessible. But the space shuttle, while tremendously capable, didn't quite live up to the vision of routine, affordable spaceflight. The program was expensive. Launches happened less frequently than anticipated. The shuttle was used primarily for missions to low Earth orbit, carrying astronauts and cargo to the space shuttle, conducting scientific experiments, deploying satellites. Meanwhile, the moon was being left to robotic exploration, and that was valuable. Orbiting spacecraft mapped the lunar surface in detail. Ground-penetrating radar revealed the presence of water ice. Spectrographic analysis revealed the composition of lunar rocks. We learned more about the moon in 50 years of robotic exploration than we learned in 50 years of human exploration. But something important was missing. There were questions that required human presence. What is the thermal properties of the lunar subsurface? What is the mechanical properties of lunar regolith? What is the radiation exposure for humans on the lunar surface? These questions required scientists on the moon asking questions and making observations. Moreover, there was a growing realization that the moon was important for the future of space exploration. If humanity was going to expand beyond Earth, the moon was a crucial stepping stone. Well, that was the question that haunted the space agencies of the world. Not, can we go back? We knew we could do that. The question was, why should we go back? What's the point? And you know what? That's actually a great scientific question to ask. The answer came slowly, over decades, as our understanding of the moon evolved. First, we realized something remarkable. The moon has water, real water, ice actually, hidden in permanently shadowed craters at the poles. Locked away from the harsh lunar sun, we discovered water ice. That changes everything, because water is not just something you drink. Water is hydrogen and oxygen, and in space those are rocket fuel. Water is the building block of survival. Water is opportunity. Then we started asking another question. What's underneath all that moon dust? What's in the rocks? And as we sent unmanned probes, rovers, and satellites to orbit and study the moon, we began to understand that the moon's surface tells a story. It tells the story of the early solar system. The impacts that shaped it reveal the history of impacts that shaped us. The rocks contain isotopes and elements that date back to the very formation of our planetary system. The moon is, in many ways, a time machine, a geological library that holds the secrets of how planets form, how solar systems develop, and how common or uncommon habitable worlds might be. And that's when it clicked. We need to go back not because we haven't been there, but because we now know the moon is important, critically important, not just for science, but for humanity's future. Think about it this way. If you're a civilization that wants to expand beyond its home planet, you need a refueling station. You need a place to test technologies. You need a training ground. The moon is 239,000 miles away, but it's only 3 days of travel. It's close enough to be reached with current technology, yet far enough to be a real challenge. It's perfect. It's the ultimate cosmic proving ground. And in February 2026, that's exactly what we're doing. But before I tell you what's happening right now, I want to make sure you understand the context. Because this isn't just about space agencies. This is about a fundamental shift in how humanity views space exploration. This is about the moment when space stopped being something only governments could do and became something that private companies, international partnerships, and commercial ventures could accomplish. This is about the democratization of space. And the moon is ground zero for that revolution. Let's start with the American effort because, frankly, that's where most of the attention is right now. NASA, the National Aeronautics and Space Administration, has been working on a program called Artemis. Now, here's a fun fact. Artemis was the twin sister of Apollo in Greek mythology. Apollo was the god of the sun, Artemis was the goddess of the moon. So NASA named their first lunar program after Apollo, and they named their return to the moon after Artemis. There's a poetic beauty to that, don't you think? The Artemis program has multiple phases. Phase 1 was about establishing a lunar gateway, a space station that orbits the moon. This gateway serves as a rendezvous point, a place for crews to dock, resupply, and prepare for the journey to the surface. It's like an orbital spaceport hovering above the lunar landscape. Phase 2, and this is where we are right now in February 2026, is about landing boots on the moon again. Real boots, real people. And this time, one of those people will be a woman. That matters. That matters a lot. Because while we celebrate the achievements of Apollo, we also need to acknowledge that Apollo was an entirely male endeavor. All 12 astronauts who walked on the moon during the Apollo program were men. In 2026, we're correcting that historical imbalance. We're sending the first woman to the moon. And that is not just symbolically important, it's scientifically important. It's culturally important. It says something about how humanity has evolved, about how we value and recognize talent regardless of gender, and about how we're building a more inclusive future in space. But here's what's really fascinating about the current lunar return mission. It's not just NASA doing this. Yes, NASA is leading the effort, but they're not alone. They're working with international partners. European Space Agency contributions, Japanese Space Agency JAXA, Canadian Space Agency, Indian Space Agency ISRO, and yes, even private companies like SpaceX and Blue Origin. This is the new reality of space exploration. It's collaborative, it's international, it's commercial. It's a far cry from the space race of the 1960s, when the United States and Soviet Union were competing tooth and nail to be the first to the moon. Now we're working together. We're combining resources, expertise, and vision to accomplish something greater than any single nation or company could achieve alone. Let me walk you through what's happening in this February 2026 mission, because the logistics of getting people to the moon are genuinely complex and fascinating. The rocket that's carrying the crew is called the Space Launch System, or SLS. It's the most powerful operational rocket in the world right now. When it launches, it produces 8.8 million pounds of thrust. To put that in perspective, that's roughly equivalent to the thrust of 17 Airbus A380 aircraft all taking off simultaneously. It's extraordinary. The SLS stands 322 feet tall. That's taller than the Statue of Liberty. And when it ignites, it doesn't gradually accelerate. It accelerates hard and fast, pushing the crew on top of it with tremendous force. The crew module sitting on top of the SLS is called Orion. Orion is a spacecraft that's been designed to go beyond the moon eventually. It can carry up to 6 astronauts, though for this lunar mission it's carrying 4. Orion is not a new design. It's actually an evolution of the Apollo Command Module, the spacecraft that carried Apollo astronauts to the moon in the 1960s and 70s. But with 50 years of technological advancement, Orion is far more sophisticated. It has modern computers, advanced life support systems, better thermal protection, and systems designed to operate in the deep space environment. The journey begins when the SLS launches from Kennedy Space Center in Florida. It's the same launch facility where the Saturn V rockets launched the Apollo missions. There's something poetic about that continuity. The same launch pad over 50 years later, sending humanity back to the moon. The SLS accelerates the Orion spacecraft to a velocity of about 25,000 miles per hour, escape velocity from Earth. And then, once they're in orbit, something remarkable happens. The spacecraft coasts. It doesn't fire constantly. It uses the physics of orbital mechanics to travel. The crew experiences a few minutes of intense acceleration, and then they're weightless. They're in freefall, but they're not falling toward Earth, they're falling toward the moon, and their trajectory is such that they'll miss the moon and end up orbiting it, or they'll do a burn to slow down and enter lunar orbit. And this is where it gets really interesting, because the moon doesn't have the kind of thin atmosphere that slows spacecraft down like Earth does. The moon has essentially no atmosphere. You can't use air resistance to slow down. So you have to use rocket braking. You have to fire your engines in reverse, which requires fuel. The Lunar Gateway orbital station I mentioned earlier, that's where Orion will dock. The crew will transfer from Orion to a lunar lander that's been waiting in orbit. And that lander is where they'll ride down to the surface. The lander being used for this mission is called the Human Landing System, or HLS. There are actually multiple companies working on lunar landers for future missions, but for this mission in February 2026, we're using a lander that's been adapted from technologies developed by a private company called SpaceX. It's called Starship HLS, Starship Human Landing System. Now, Starship is an ambitious vehicle. It's designed to be fully reusable. In the long term, the vision is that Starship will be used to land humans on Mars. But right now, it's being tested and adapted for lunar landings. Here's how it works. The crew ascends from Earth in Orion. Orion rendezvous with the Gateway. The crew transfers to Starship HLS, which is waiting in orbit. Starship HLS then performs a powered descent to the lunar surface. And here's where the lunar environment really matters. The moon has only 1/6 the gravity of Earth. That means the same rocket produces 6 times more deceleration on the moon than it would on Earth. So Starship is able to land with much less propellant than it would need for Earth landing. The landing is still complex. You need to avoid boulders, manage fuel carefully, and stick your landing precisely, but it's achievable with relatively modest engines by modern standards. Once Starship lands, the crew suits up. They're wearing modern spacesuits that are far more advanced than the suits Apollo astronauts wore. The suits have better thermal protection, better mobility, better communications, and integrated life support systems. They've practiced these suits in neutral buoyancy tanks on Earth, which simulate the 1/6 gravity of the Moon quite well. They've trained extensively. They're ready. And then they step out. That first step. That first human footprint on the lunar surface in more than 50 years. That moment will be witnessed by millions of people around the world. And the cameras transmitting that image, they'll be in high definition. They'll be in color. They'll be transmitted in real time via satellite. We'll all watch it live. We'll see the boots landing on the regolith, that's lunar dust. We'll see the lunar module behind them. We'll see the black sky of the airless moon. We'll see Earth hanging in that black sky above the lunar horizon. And we'll feel the weight of that moment. But here's where it gets really important. Because once they're down there, they're not just looking around and taking pictures. Well, they're doing that. But they're also working. They're conducting experiments. The lunar location being selected for this February 2026 landing is in the South Polar region. That's deliberate, because the South Polar region of the Moon is special. It contains permanently shadowed craters. These are regions where the sun never shines. And because the sun never shines, the temperature in these craters drops to around -370 degrees Fahrenheit. That's cold enough to preserve volatile materials, compounds that would normally boil away in sunlight. And hidden in these cold traps is water ice. Lots of it. Potentially billions of tons of it. Now, why does that matter? Because water is transformative. If you have water, you have hydrogen and oxygen. You can split water into its components using electrolysis, something we've known how to do for centuries. And hydrogen and oxygen are rocket fuel. If you can establish a base on the Moon and extract water from that ice, you can produce fuel on the Moon. You can refuel spacecraft on the Moon. That means a spacecraft doesn't need to carry all its fuel from Earth. It can refuel at the Moon. And that changes the economics of space travel forever. The crew landing in February 2026 will be conducting experiments focused on water ice. They'll be using ground-penetrating radar to map ice deposits. They'll be collecting samples. They'll be testing drilling techniques. They'll be evaluating the feasibility of water extraction. This isn't just tourism. This is reconnaissance. This is preparatory science for establishing a permanent human presence on the Moon. And you know what the most remarkable part is? This isn't a one-time mission. There are plans for follow-up missions. Every few years, more crews will land. More samples will be collected. More science will be done. More technologies will be tested. The vision is a sustained presence on the Moon. Not a brief visit, but a long-term commitment. That's the American side of things. But remember, I said this is an international effort. Let me tell you what's happening with other nations. China has been absolutely remarkable in their lunar exploration efforts. They've been landing rovers and landers on the Moon consistently. While the American Artemis program was being developed, China was doing something equally impressive. They were actually landing people-equivalent payloads and rovers on the lunar surface. China's lunar exploration program is officially named after the Chinese moon goddess Chang'e, and their long-term goal is clear: establish a permanent human presence on the Moon. China is aiming to land astronauts on the Moon by the late 2020s or early 2030s. And they're not just planning to visit. They're planning to build. They're planning to construct a lunar research station. Now, there's something interesting here. China and the United States aren't competing in the same way the Soviet Union and United States competed in the 1960s. Yes, there's a space race happening, but it's a different kind of race. It's a race to show capability, to demonstrate technological prowess, to be recognized as a major spacefaring nation. And that race is actually benefiting humanity overall because it's driving innovation and investment in space exploration. The European Space Agency has a different approach. ESA is focusing on supporting the Artemis program and developing key technologies like the Lunar Gateway logistics modules and advanced spacesuits. ESA recognizes that Europe's strength in space lies in technological innovation and collaboration. Rather than competing with the United States, ESA is partnering with NASA and other agencies to achieve shared goals. Japan's JAXA has been particularly innovative. They've sent rovers to the moon, and they're developing technology for lunar resource utilization. And India's space program, ISRO, has successfully landed rovers on the moon, and they're planning more ambitious missions. India's approach is economically efficient. They've demonstrated that you don't need massive budgets to accomplish lunar exploration. You need smart engineering and focused objectives. And then there's the private sector. SpaceX is not only developing the Starship HLS, they're also launching lunar landers for other companies and government agencies. Blue Origin, Jeff Bezos' space company, is developing lunar landers and long-term moon-based concepts. There are smaller companies too. Axiom Space is building commercial space stations. Relativity Space is using 3D printing technology to manufacture rocket components. Axiom and other companies are working on commercial space modules that could be added to the Lunar Gateway. This is the new landscape of space exploration. Government agencies provide the foundational capabilities and vision. Private companies provide innovation, competition, and efficiency. And together, they're creating an ecosystem in space that makes human settlement beyond Earth increasingly possible. Let me talk about what the actual landing site looks like, because this is fascinating. The moon isn't flat. People sometimes imagine the lunar surface as this uniform, barren plain. But that's not accurate. The moon is geologically complex. There are mountains as tall as the Rockies. There are valleys and canyons. There are impact craters of all sizes, from microscopic pits to massive basins hundreds of miles across. And at the poles, particularly the South Pole, the terrain is especially rugged. The landing site selected for this February 2026 mission is near a crater called Aitken. More specifically, it's in a region near the rim of the South Pole Aitken Basin. This basin is one of the largest impact craters in the entire solar system. It's over 1,200 miles in diameter. And at its center, or near its center, is some of the most interesting geology on the moon. The permanently shadowed craters in this region are what we call cold traps. Imagine a crater that's deep and steep-sided. The crater is oriented such that the sun's rays never reach the bottom. It's always in shadow. Over billions of years, water molecules that arrived on the moon via comets and asteroid impacts have accumulated in these cold traps. They've frozen solid. They're waiting there, preserved in deep freeze like a time capsule from the early solar system. Now, here's a remarkable thing. We know this water is there because we've detected it from orbit. Multiple spacecraft have identified the signature of water ice using infrared instruments and neutron detectors. But seeing it from orbit and actually touching it are two different things. That's why the crew landing in February 2026 needs to go down there. They need to measure it directly. They need to collect samples. They need to understand not just that the water is there, but how much, what form it's in, how concentrated it is, and most importantly, how accessible it is. Because here's the reality. If water is locked in crystalline rock, embedded deep in the regolith, it's hard to extract. But if it's more loosely bound to the soil, if it's in pockets and veins, it's easier. The difference might mean the difference between a moderately difficult extraction process and an impossibly expensive one. So finding the right deposits is critical. The landing site also has been selected for other reasons. It has visibility from Earth, which means communications with the crew will be good. It has relatively gentle slopes near the actual landing point, which makes landing safer. And it's close to multiple permanently shadowed craters, which means the crew can explore and sample multiple locations. It's not an easy landing site. The South Polar terrain is inherently challenging, but it's been carefully selected based on orbital imagery and mission planning. When the crew lands, they'll have a specific timeline. On the moon, a lunar day lasts about 14 Earth days. The crew will be operating during the lunar day, when the sun is visible. But they're landing near the pole, so the sun's angle is low on the horizon. The lighting is going to be challenging. Shadows will be long. And just beyond them, just a few miles away, are those permanently shadowed craters. Craters where the temperature is below -370 degrees. Craters where a spacesuit malfunction could be fatal within seconds. This is serious business. This isn't entertainment. This is exploration at the edge of human capability. The crew will have pressurized rovers. These aren't little moon buggies like Apollo crews used. These are more like vehicles. They're pressurized, meaning the crew can sit inside without wearing full spacesuits. They have redundant life support systems. They have navigation systems. They can travel several miles from the landing site. The crew will use these rovers to reach sampling sites, conduct experiments, collect data, and return to the lander before sunset. Because here's the thing about the moon. A lunar night lasts 14 Earth days. During that time, there's no sunlight. The temperature drops to -370 degrees. No spacecraft designed for human habitation has been left on the moon to survive a lunar night. Well, not yet. So the crew has to return to the lander before sunset. The lander will be powered by fuel cells and batteries, but it's designed for a crew to shelter in it for maybe a few days, not 2 weeks. So this mission is a daytime operation. The crew lands during the lunar day, they work for about 7 to 10 days, and then they ascend back to orbit and return to Orion. But here's where the future gets interesting. Future missions, once we've established more infrastructure and better habitats, will be longer. Crews will stay for weeks, then months. Eventually, you'll have crews rotating through a permanent base. But this February 2026 mission is a proof of concept. It's demonstrating that we can land, we can work, we can gather science, and we can safely return. Now let me talk about the specific science being conducted. The first and foremost priority is water ice mapping and characterization. The crew will use ground-penetrating radar to map the subsurface. This radar will penetrate the lunar soil and create an image of what's underneath. If there are ice layers, the radar will detect them. The crew will also drill. They'll bring drill equipment to extract samples from depth. These samples will tell us what form the ice is in, how pure it is, what other materials are mixed with it. They'll take spectrographic measurements, which will tell them the chemical composition of the ice. And they'll bring samples back to Earth, where they can be analyzed in detail in laboratories. The second priority is geological sampling. The South Polar region sits on a very old part of the moon. It's also at the edge of the South Polaican Basin, which means there's impact-derived material from deep within the moon. Material that came from the lunar interior during the ancient impact that created the basin. By analyzing these samples, lunar geologists can understand what the moon is made of, how it differentiated into layers, and what materials are available. This is foundational knowledge for any long-term lunar settlement. The third priority is equipment testing. The crew will be testing new technologies that will be used on future missions. Prototype extraction equipment, prototype habitat modules, advanced radiation shielding, life support system components, mining equipment. All of these will be tested in the actual lunar environment. Because lunar simulations on Earth are good, but they're not perfect. The actual lunar environment has real dust with abrasive properties. It has real radiation. It has real thermal stresses. Equipment needs to be tested there. The fourth priority is psychological and physiological studies. The crew are humans in the lunar environment. Scientists want to understand how the human body and mind perform there. They'll be conducting experiments on themselves, measuring bone density loss, muscle loss, and how exercise can mitigate these, measuring psychological factors, evaluating fatigue, stress, and decision-making. This is data that will be crucial for longer missions and eventual human settlement on the moon. The fifth priority is operational experience. The crew and mission control need to learn how to work on the moon. What tasks take longer than expected? What equipment is problematic? What procedures need refinement? This mission is not just about collecting science. It's about learning how to operate effectively in this alien environment. That operational knowledge is invaluable for future missions. All of this is happening over maybe 10 days. It's a compressed timeline, but it's a crucial mission. It's the bridge between the Apollo era and the settlement era. Now let me tell you something that's really important to understand about this whole effort: the cost. The Artemis program, the entire program including development, testing, and missions through establishing a lunar gateway, costs roughly $100 billion over 2 decades. Now, that sounds like a lot of money, and in absolute terms, it is. But context is important. That's spread over 20 years. That's about $5 billion per year. The entire NASA budget is about $25 billion per year. So Artemis is roughly 20% of NASA's total budget. For comparison, the total spending on space-based satellites, space tourism, and all commercial space activities in the United States is hundreds of billions of dollars. The military spending on space-related systems is tens of billions of dollars annually. When you look at it that way, the Artemis program is not an extravagant expense. It's a focused, sustained investment in one of the most ambitious scientific and engineering endeavors in human history. It's comparable to major infrastructure projects on Earth. The interstate highway system cost about $500 billion in today's dollars. The Apollo program cost about $280 billion in today's dollars. Artemis is less expensive than Apollo was, despite being more ambitious, because technology has improved and our methods are more efficient. But here's the thing that's really important. This isn't money being wasted. It's money being invested in human capability, knowledge, and future possibility. Every dollar spent on Artemis supports engineers, scientists, contractors, and businesses. It drives technological innovation that has spin-off benefits in other areas. The spacesuits being developed have better insulation and mobility systems that could benefit workers in extreme environments on Earth. The rover technology being developed could be adapted for rescue and exploration on Earth. The life support systems could be used in submarines or deep-sea habitats. The mining and extraction techniques being pioneered could be applied to mining operations on Earth. This is how innovation works. You push the boundaries in one domain, and the knowledge and technology spill over to other domains. The Apollo program gave us satellite communications, cordless tools, and advanced materials. Artemis will give us even more. Now, I want to talk about one more aspect of this mission that's incredibly important: the geopolitical dimension. For most of the space age, space exploration was dominated by superpowers. The United States and the Soviet Union competed, and other nations watched. That era has ended. Now, space is increasingly democratic. Nations of all sizes are participating. Companies are participating. International organizations are participating. And the moon is becoming a focal point of this new era. The Artemis program explicitly includes international partners. NASA made a conscious choice to work with other space agencies rather than compete. This creates stability, creates shared interests. When nations work together on the moon, they're less likely to be in conflict on Earth. Not guaranteed, the geopolitical situation is complex, but there's definitely a stabilizing effect. There's also an important agreement that governs lunar activities. It's called the Outer Space Treaty, signed in 1967. It states that no nation can claim ownership of celestial bodies. The moon is the province of all humankind. No one can own the moon. But this doesn't mean there's no property rights. The question of property rights and resource rights on the moon is becoming increasingly important, and there's active discussion in the international community about how to handle it. The basic principle being discussed is that if you extract resources from the moon, if you mine water ice, for example, you own the water that you extract. But you don't own the location you extracted it from. It's similar to how deep-sea minerals work in international waters. You can harvest them, but you don't own the seabed. This is important for the commercial development of space. If companies are going to invest billions in lunar mining operations, they need some assurance of property rights. Without that, investment won't happen. The international community is working toward a framework that allows commercial activity while respecting the principle that the moon belongs to all humanity. Here's another aspect that's fascinating: the timeline. Why is this landing happening in February 2026? Well, launch windows to the moon are determined by orbital mechanics. The moon's position relative to Earth changes. The optimal windows for a lunar transfer occur roughly every month or so. But for a landing in a specific location, you need the right combination of orbital geometry, lighting conditions, and other factors. February 2026 represents a good launch window with good lighting conditions at the South Polar landing site. If the launch were delayed, the next good opportunity might be several months away. And with a program like Artemis, you have launch windows built into the schedule, and you work toward them. The timeline is also driven by the pace of spacecraft development. The Artemis 3 mission, because yes, this first human landing is being called Artemis 3, Artemis 1 was an uncrewed test of Orion, and Artemis 2 will be a crewed lunar flyby without landing, has been in development for years. Hardware is being built. Tests are being conducted. The mission date of February 2026 is based on the pace of development and the readiness of spacecraft and crew. This timeline is ambitious but achievable. NASA has hit this kind of timeline before. During the Apollo program, they were landing humans on the moon every few months at their peak. They had the machinery, processes, and people in place. For Artemis, the timeline is longer because we're building new systems for a different era. But the fundamental pace is manageable. Now, let me paint a picture of what the actual mission will look like from the perspective of someone watching it unfold. It begins with a launch announcement. Days before the launch, NASA holds a press conference. The mission details are explained. The crew members address the media. They talk about their motivation, their preparation, their excitement. The world pays attention. News outlets around the world begin covering the story. Schools plan watching parties. Families gather to watch the broadcast. Launch day arrives. At Kennedy Space Center, the SLS rocket stands on the launch pad. It's visible for miles around. The rocket is 322 feet tall, and it's painted white with blue and red accents. It's a beautiful piece of engineering. The crew has already been brought to the launch pad. That happened a few hours earlier in a specially designed convoy. They walked up the elevator to the Orion capsule and strapped in. They've checked every system. They're ready. In mission control in Houston, dozens of flight directors, engineers, and specialists are monitoring every system. In data centers across the United States, computers are running final verification programs. In the viewing areas, thousands of people have gathered, family members of the crew, NASA employees, school groups, tourists. The energy is electric. At T-minus 60 seconds, the automated countdown begins. No human can stop it now. The computers are in control. The launch window is narrow, maybe a few seconds wide. If the rocket doesn't launch within that window, the mission is postponed. T-minus 10 seconds. The main engines are ignited. They don't immediately produce full thrust. They spin up. The engines are like enormous turbines, burning liquid oxygen and liquid hydrogen. The ignition happens. T-minus 3 seconds. The solid rocket boosters ignite. This is it. The moment when everything changes. The SLS rocket produces 8.8 million pounds of thrust. The rocket doesn't instantly accelerate. There's a moment where the thrust is just equal to the weight. The rocket sits on the pad, engines roaring, building pressure, building thrust. T0. The rocket is released. The hold-down arms release. And the rocket, carrying the Orion spacecraft and for humans, begins to rise. For the first few seconds, the acceleration is gradual. The rocket is moving against gravity. Every foot it rises has to be fought for. But the engines are powerful, and the acceleration increases. By the time the rocket has risen 100 feet, it's accelerating at about 1.2 g, about 20% more than Earth's gravity. The crew feels pushed into their seats. By the time the rocket rises a mile, it's accelerating at 2 g. The crew feels twice their normal weight pressing down on them. It's like lying in a strong centrifuge. The view from the crew compartment is changing. The ground is falling away. The curvature of the Earth is becoming visible. 2 minutes after launch, the solid rocket boosters burn out. The rocket has risen about 45 miles. It's out of the dense lower atmosphere. The acceleration drops as the boosters separate. They're no longer contributing thrust. But the main engines of the SLS, the core stage, are still burning. The acceleration builds again. By 6 minutes after launch, the core stage is burning out. The rocket has reached about 70 miles of altitude. The velocity is approaching 17,000 miles per hour. The crew is weightless now. The acceleration is gone. The rocket engines have shut down. There's a moment of silence, a spectacular moment where the crew can experience freefall, where they can look down at Earth falling away below them. Then the upper stage reignites. The second stage of the SLS, called the Interim Cryogenic Propulsion Stage, or ICPS, burns to accelerate the crew further. This burn takes about 16 minutes. During this time, the crew watches. They listen to the communications with mission control. They feel the subtle vibrations of the rocket. They know they're approaching escape velocity from Earth. When the ICPS burns out, the crew is in Earth orbit. They're orbiting about 100 miles up, at a velocity of about 17,500 miles per hour. At this speed, they're falling around the Earth. They're in orbit. It's a remarkable feeling, floating weightless while hurtling around the planet. The crew has about an hour in this orbit. They check systems. They ensure everything is functioning correctly. Mission control verifies that the spacecraft is healthy. There are no anomalies. Then the ICPS performs a translunar injection burn. This is not a big burn, only about 15 minutes of engine time. But it's the crucial burn. It adds just enough velocity to the spacecraft that instead of falling back to Earth or remaining in Earth orbit, the spacecraft will travel to the Moon. The velocity is now about 24,500 miles per hour, escape velocity from Earth. And then they're on their way. The journey takes about 3 days. The crew doesn't need to do much during this time. The trajectory is ballistic. It's been calculated and set. The spacecraft is following a path determined by gravity. The crew can rest, exercise, eat, perform checks on the systems. They can look out the window and watch Earth getting smaller. By the second day, Earth appears as a sphere of blue and white hanging in the black of space. By the third day, it's like a large marble. It's a perspective that changes people. That view of Earth from space, that realization that you're so far from home, it's transformative. On day 3, as the spacecraft approaches the Moon, the view changes. The Moon grows larger. It's no longer a point of light. It's becoming a world. The crew can see the craters. They can see the mountains. They can see the locations they're about to visit. The spacecraft is being pulled by lunar gravity now. It's slowing down as the Moon's gravity becomes dominant. When they're still tens of thousands of miles away, the Moon's gravity is slowing them down from 24,500 miles per hour. They're decelerating not rapidly, but consistently. Eventually, the spacecraft is close enough to the Moon that the crew performs a lunar orbit insertion burn. The engines fire. The deceleration increases. And then, suddenly, they're in orbit around the Moon. It's a moment that previous astronauts have described as profound. You're orbiting another world. You're 239,000 miles from home. You can see the entire lunar disk spread out below you, mountains and craters and vast flat plains. And right there, hanging above the lunar horizon, is Earth. A blue dot hanging in the black of space. A cosmic perspective. The crew orbits the Moon multiple times. They're looking at the landing site. They're checking weather conditions, lunar weather. Dust storms aren't an issue on the airless Moon, but other factors matter. Lighting, communications, trajectory calculations. Everything has to be perfect. Then, at a designated time, the crew suits up. They enter the Starship HLS lander that's waiting in orbit. They check all the systems in the lander. They verify that the life support is functioning, that the propulsion systems are ready, that the landing computers are programmed correctly. And then they undock from Orion. For a moment, the Orion spacecraft and the Starship lander separate. 2 spacecraft orbiting the Moon together, then drifting apart. The lander begins its descent sequence. Here's where it gets really intense. The lander is now committed. They're not going back to Orion. They're going down to the Moon. The computers begin firing the descent engines. The spacecraft is traveling about 3,600 miles per hour in orbit. The engines need to slow it down so that by the time it reaches the surface, it's moving only a few miles per hour. The descent takes about 15 minutes. During that time, the crew is in communication with mission control. They're receiving navigational data. They're getting information about the terrain below. The view out the window is spectacular and terrifying simultaneously. The Moon is rushing up toward them. The craters are becoming larger. The horizon is becoming curved. The sun is low on the horizon. Remember, they're landing near the South Pole, and the shadows are long and black. The lander is now in the final phase of descent. It's about 1,000 feet up. It's slowing down. The computers are making fine adjustments to the trajectory. The crew is monitoring everything. They can see the landing site now. They can see the exact spot where they're going to land. The lander is now 100 feet up. It's moving at about 50 miles per hour. The engines are firing hard, pushing the spacecraft down and back up, slowing the descent. Dust is being kicked up from the lunar surface, not an atmosphere of dust, but individual particles being blown by the rocket exhaust. The lander is now 50 feet up. The computers are still making adjustments. There might be a boulder in the projected landing area. The computer might command the lander to move slightly left or right to avoid it. This kind of precision landing is what makes modern lunar landings possible. The lander is now 20 feet up. The descent rate is just a few miles per hour. The landing legs are down. The crew can see the lunar surface through the small windows of the lander. It looks gray and lifeless. It looks ancient. It looks exactly like the moon. The lander is now 10 feet up. 5 feet. 3 feet. Contact. One of the landing legs touches the surface. The lander settles down. It's stable. The engines shut off. The lander has landed on the moon. For a moment, there's silence. In mission control, there's a moment of checking, verifying that all systems are stable, that there are no problems, that everything is good. And then celebration. The flight control room erupts. People are shaking hands, hugging, raising their fists in the air. The cameras capturing this moment show joy, relief, pride. A human spacecraft has landed safely on the moon for the first time in over 50 years. In the spacecraft, the crew is also experiencing this moment. The acceleration is gone. They're no longer being pushed. The engines are silent. They're sitting on the moon. They're on another world. Through the small window, they can see the gray lunar surface. They can see rocks and dust. They can see the landing site they trained for. They don't have much time to dwell on it, though. There are procedures to follow. They check the spacecraft systems one more time. They confirm that the landing gear is stable. They verify that the ascent stage is ready to launch them back to orbit later. They check the life support systems. They prepare the airlock. And then one of the crew members opens the hatch. It's the first woman to step on the moon. She's already made history by being selected. But now she's going to step through that hatch and onto the lunar surface. She climbs down the ladder. The ladder is narrow and steep. It's about 10 feet to the ground. She comes down one rung at a time. The gravity is light 1/6 Earth's gravity. Every movement is careful and controlled. Her boot touches the regolith. Her weight is distributed across the surface. She's standing on the moon. Behind her, over the next few minutes, the other crew members follow. One by one, they descend the ladder and step onto the lunar surface. Now there are 4 humans on the moon. 4 voices in communication with each other and with Earth. 4 sets of boot prints in the regolith. For people bearing witness to this moment. The first words spoken on the moon in more than 50 years will be different than Neil Armstrong's famous words 57 years earlier. Armstrong said, "That's one small step for man, one giant leap for mankind." The words were poetic, planned in advance, meaningful. The words spoken on this mission will likely be more focused on the task at hand. Something like, "Lunar surface, Houston, the primary lunar module is solid. We're beginning EVA preparations." Professional, focused, scientific, but they carry the same weight. They represent the same achievement. Humans are on the moon. The crew spends the next few minutes adjusting to the environment. The suits are working correctly. The life support systems are functioning. The communications are clear. They perform a systems check. They ensure that everything is functioning as designed. Then they begin unloading equipment. The Starship lander carries equipment in its cargo bay. Rovers, drill equipment, scientific instruments. All of this needs to be unloaded and prepared. The crew works methodically. On Earth, each of these tasks takes a few minutes. On the moon, in a spacesuit with limited visibility and mobility, it takes longer. What might take 30 seconds on Earth takes 3 minutes on the moon. But the crew is trained. They've practiced these exact tasks in simulations. They know what to do. They work with purpose. The first thing they do is deploy the rover. The rover is a pressurized vehicle, roughly the size of a large SUV. It has wheels that are specially designed for the lunar terrain. It has life support systems inside so the crew can sit without full spacesuits. It has a navigation system, communications equipment, and battery systems. The rover takes about an hour to fully deploy and check out. The crew drives it around the landing site in a test loop, verifying that all the systems work, that the navigation is accurate. And then they're ready to begin their primary missions. The first mission is to reach the nearest permanently shadowed crater. This crater is about 5 miles from the landing site. In the rover, traveling across the lunar terrain, this will take roughly 2 hours of careful driving. The terrain isn't smooth. There are boulders, craters, and uneven ground. The rover has good traction. The wheel design has been optimized for lunar soil, but it's still challenging. As they drive, the crew is seeing things that only a handful of humans have ever seen. The lunar landscape is like Earth's deserts, but unlike anything on Earth. The sky is black even though it's daytime. The stars are visible. The sun is low on the horizon. Shadows are harsh and black. There's no atmospheric haze to soften the view. Everything is sharp and clear and alien. The terrain around them tells a story. The South Polar region has been shaped by billions of years of impacts. Each crater was created by an asteroid or comet impact. The oldest craters have been partially buried by more recent impacts. The terrain is complex. From orbit, scientists have mapped the area carefully. The crew has studied the maps. They know approximately where hazards are, where good terrain is, where the permanently shadowed craters are. After about 2 hours, they approach their first target crater. It's a crater about a mile in diameter. The rim rises about 1,000 feet above the surrounding terrain. The interior of the crater is dark, permanently shadowed. The crew can't drive into it. The sides are too steep, but they can drive to the rim and look in. From the rim, they deploy instruments. They set up the ground-penetrating radar. They take spectrographic measurements. They might collect rock samples from the rim, samples that have been melted or altered by the impact that created the crater. But they're looking for ice evidence. The ground-penetrating radar is the key instrument. It sends radio waves into the lunar subsurface. Where there's ice, the radar reflects differently than where there's just rock and dust. The crew operates the radar, sweeping it across the crater floor and walls. Mission Control is receiving real-time data. Scientists are analyzing the data as it comes in, and then they see it. There's a strong radar signature consistent with water ice. The ice is mixed with regolith, but it's there. It's concentrated enough to be detected. The mission is working. This is real data. This is proof of concept that water ice can be detected and analyzed by human crews on the moon. The crew spends several hours at this location. They take multiple measurements. They collect samples, both samples from the rim and samples drilled from depth, showing the transition between ice-rich regolith and regular regolith. The samples are packed into a special sample collection box. These samples will be brought back to Earth. Then, they begin the drive back to the landing site. It's late in the lunar day now. The sun is getting lower. The shadows are getting longer. The lighting is becoming more challenging. But they make it back to the lander before the end of the workday. The crew is tired, not physically, because the lower gravity makes physical exertion less demanding, but mentally tired. They've been doing high-focus work in an alien environment while wearing spacesuits and relying on life support systems. It's exhausting. They unload their samples. They shut down the rover. They perform a check of the lander systems. Then they enter the airlock. The airlock is depressurized. The pressure is slowly reduced from whatever atmosphere they're maintaining around the lander to the vacuum of the moon. As the pressure drops, any water vapor or other atmospheric content would be lost. But the pressure is slowly reduced, and the crew opens the hatch to the interior of the lander. Now they're inside the pressurized cabin. They remove their spacesuits, a complex process involving helping each other out of the suits. checking for any damage, ensuring that the suits are properly stored and will be ready for the next EVA. They drink water. They eat. They check their physical condition. Medics are monitoring them remotely, watching their vital signs, ensuring that they're healthy. They sleep. The lander has sleeping quarters. Not comfortable by Earth standards, but functional. The crew rotates who sleeps when, maintaining a watch schedule. The lander is equipped with alarms and automated systems, but someone is always awake. This pattern continues for several days. Days are spent on the lunar surface, conducting science, collecting samples, testing equipment. Nights are spent in the lander, analyzing data, preparing equipment for the next day, resting. On the final day, the crew prepares for ascent. They pack the samples carefully. They ensure that all critical equipment is secured. The ascent stage of the lander, the part that contains the engines and will carry them back to orbit, is checked one final time. Everything has to be perfect. If there's a failure during ascent, there's no rescue available. The crew must be able to reach orbit. The final EVA is brief. They perform one last set of measurements. They leave behind a commemorative marker, a flag or plaque or some symbol of human exploration. They take one last look around at the landscape. They take one last set of photos. And then they return to the lander. They pressurize the airlock. They remove their suits. They secure the hatch. They complete the procedure to jettison the descent stage of the lander, the part that served as their shelter on the surface. This descent stage will remain on the moon forever. It will be part of the lunar landscape, a monument to human presence. The ascent stage is now free to launch. The engines are checked one more time. The trajectory is calculated and verified. The crew is strapped in. They have a launch window, a specific time when they need to launch to reach the right trajectory to meet up with Orion in orbit. The countdown begins. The engines ignite, and the lander ascends. It's a violent acceleration. The crew is pushed hard into their seats. The acceleration is about 1.5 g more intense than their weight on the moon, less than their weight on Earth. The lander rises. The lunar surface falls away. Through the window, they can see the landing site below them getting smaller. The horizon curves. The curvature becomes more pronounced as they climb. The ascent burns for about 6 minutes. By the time it's finished, the lander is in lunar orbit, traveling at about 3,600 miles per hour. The crew is weightless. The engines are off, and they're heading toward a rendezvous with Orion. The rendezvous takes about 6 hours. During this time, the crew performs orbital mechanics maneuvers. They adjust their velocity and trajectory. They're being guided by computers and by communications with mission control. Eventually, they see Orion ahead of them. The spacecraft that carried them here is waiting. They approach slowly and carefully. Every movement is controlled. This is one of the most critical moments of the mission. If something goes wrong during the rendezvous, if they miscalculate, if there's a communications failure, they could miss Orion and end up drifting in lunar orbit with no way to reach it. But the procedures are well rehearsed. They've been done many times in simulation. The final approach is automated. The computers are flying the rendezvous. The crew is monitoring. Contact. The ascent stage docks with Orion. Mechanical clamps engage. The spacecraft are now connected. There's a series of verifications, checking that the docking is secure, that seals are intact, that all connections are correct. Once everything is verified, the crew begins transferring from the ascent stage to Orion. They transfer the sample containers first. The lunar samples are precious. They're the entire scientific payload of the mission. Once they're safely in Orion, the crew transfers. Now all 4 crew members are in Orion. The ascent stage is no longer needed. It's undocked and left in lunar orbit to drift forever. The crew is now in the spacecraft that will bring them home. They check the spacecraft systems. They verify that the journey to Earth is planned correctly. And then they wait. The wait might be several hours or even a day. It depends on the optimal launch window for a return trajectory to Earth. When the window arrives, the Orion engines ignite. The spacecraft is given a push, adding just enough velocity to put it on a trajectory back to Earth. The moon's gravity releases them, and they're on their way home. The journey back takes about 3 days. Like the journey out, it's mostly coasting, following ballistic trajectories. But now, instead of Earth getting smaller, it's getting larger. From a marble-sized disk, it grows larger every day. By the second day, it's noticeably larger, showing its continent